talk is about Painlevé equations and powerful tool to work with, which is called the space of initial data. For the most part of my talk, maybe not the most, but the half of my talk, I will follow paper by Kajibara, Naomi, Yamada, Geometrical Aspects of Painlevé Equations. Here it's hexagonal. So it's like a review. So so here is a brief plan of my 2 segments. So I will start from speaking about Painlevé equations and connecting my talk with Pasha's talk. Then we will construct space of initial data on the example of Painlevé IV equation with blowup. So here I will explain what is blowup. Then I think it will be already at the second talk. We will have some algebraic geometry stuff to formulate the geometric properties of space of initial data more generally. More algebraic, more impressive. So and finally, I think this will be the biggest part. I will talk about the Sakai classification of Painlevé equations, which covers Painlevé equations and q-Painleve equations, and also d-Painleve equations, and the more general LDEq one. But this will be surely at the second talk. Okay, so let's start. Pasha said that for the Pasha speaks about the monodramic problem of the following linear problem, where Z is sum of A Z minus A. And he said that the most simple non-trivial case of this is the monodramic problems leads to Painlevé VI equation. So this is n equal to, so this is SL2 A of Z with 4 points. This is the most simple non-trivial case of this monodramic problem, because if you take 3 points, we will have hypergeometry case. Okay, so when we have 4 points on the sphere, when we have 4 points on the Riemann sphere, its positions it is essentially enough to move only 1 point, because up to rational, up to Möbius transformations, we can put 3 points in points 0, 1, and infinity. So we have only one. In this problem, we have only one exception, one essential parameter. It is parameter t, position of the force point, and we want to only this point. So, and in this case, the Schlesinger equations will be as follows: dt a0 is commutator of at a0 over t. dt a1 will be commutator of at a1 over t minus 1, and dt a and dt a infinity will be 0. Yes, because if we tend the point, so it should be something like at commutator ar, if we put here not infinity but r, at ar over t minus r. This goes to 0 when r goes to infinity. So a infinity goes to a infinity becomes constant. A infinity is constant. And so on. We have that because a0 plus at plus a 1 should be equal minus a infinity. Yes, because we have Riemann sphere, and sum of the residue should be 0. We have that dt at equal minus at a0 over t minus at a1 over t minus 1. So we have we have such dynamical system on 3 matrices, and it appears that this system is equivalent to the Painleve VI equation. In what sense? Let's calculate how many essential parameters we have in this system. What I mean? When we speak about the monodromic deformation, we fix the eigenvalues of matrices A. So for matrix IE, eigenvalues will be theta E minus theta E. Yes, because it's essential matrices. So and so the first non-essential freedom that we can remove is diagonalization by matrix conjugation. So we then make A infinity. We can make A infinity became So now we know A infinity precisely, because it's constant. It will be always diagonal with such eigenvalues. So next, we see that AT, for example, AT, is defined by this equation and two matrices, A0 and A1. How many parameters have A0 and A1? Each of them has two parameters. Why? Because both they are SLD2, so minus one parameter. All parameters is complex, of course. We have one condition, it is trace condition, and another condition that we know the eigenvalues. Yes, so here it is theta 0 minus theta 0, here it is theta 1 minus theta 1. So we have four now we have four parameters, but we have also condition for the eigenvalue of this matrix, which appear from this equation. So four parameters, we have minus one eigenvalue of this matrix, which we obtain from this formula, and also we have another essential freedom, which is conjugation by diagonal matrix, because it commutes with this diagonal matrix. So we have also minus one from this. So finally, such maybe something naive calculation give us that this equation is in fact the dynamics only on two functions, because other matrix coefficients could be expressed in principle in terms of these functions. And it appears how we can choose these functions. How it's natural to choose. We can take element 1, 2 of matrix AZ, which is sum of these A's with poles. And what we see here we know the denominator. Yes, it is all of the poles. Yes, when we collect. But what we have in the numerator? In the numerator we have also a polynomial. Can it be of order 2? No, because we know that A infinity, which is the sum of all of this matrix, have 1, 2 coefficient 0. That's why here we have polynomial of order 1, and it has a 0. We denoted 0 by t. Also, here is some coefficient, and using the freedom of conjugation by diagonal matrix, we can choose it as we want. It is chosen like t minus 1. Okay, so we can also choose
Anton, you have 4 black. So
sorry?
you can use the other 3 blackboards.
Yeah, of course, but okay, so I can take one function q, one function q as follows, and another function b is something about a11z in point z equal to qt. So I'm afraid that the precise formula is could be rather complicated. So so we have so our system, in fact, it's system on two functions, p and q. Yes. And this system is called Painleve VI. So and it appears in fact this is not a wonder, but this is not a miracle, but maybe I want to avoid explaining why, because it's not the topic. It appears that that we can choose this choice of p and q give us that this is some non-autonomous Hamiltonian system with Hamiltonian as follows: q minus 1 minus 1 h6 is q minus 1 q minus p minus 2 minus over q minus 2 theta q minus 1 over q minus p minus 2 theta 1 q minus 1 plus theta 0 plus theta t plus theta 1 plus theta infinity, theta 0 plus theta t plus theta 1 minus theta infinity minus 1 q minus t. So you see that this is non-autonomous Hamiltonian because it depends. It essentially depends on t in many places. Here, of course, you can see that I write for some reasons not q but q minus t, but it's for my this term is unessential for the equations, but it will be essential for some of my future calculations.
So isn't the same Hamiltonian as the one that defines tau function, or it depends on by some t dependent?
No. There are some. So to define tau function, which is given as a standard sum of partition functions, you should make some background transformation with this Hamiltonian.
But with background transformations only shift thetas by some integer or half integer numbers.
No, background transformation can change Hamiltonian.
Well, of course, but
not only in the way as you say.
But isn't it true that any Hamiltonian should define some tau function, and the only question is, well, what are the parameters of this tau function?
Yes, I think yes. This is more. This background transformation is more about some normalization, some convenience. Standardly, Painleve VI equation is written as a second order nonlinear equation obtained by eliminating B from this Hamiltonian system. But I don't want to write it. Okay. So this is a brief scheme how Painleve VI equation appears from the isomonodromic deformation. So, in fact, I cannot present this calculation of this P and Q because it is very, not very, but rather tedious. So. Questions? So if no, I will then I will pass to the next point about Painleve equation coefficients. So initially Painleve equations appeared not as not from the isomonodromic problem. But as a problem to describe differential equations of second order, which solutions have no movable singularities, and singularities in this case means essential singularities or branching, so pulse is not considered as a singularities. And the classification and this classification give us as Painleve VI equation, Painleve VI equation, and also some another equations which have less than 4 parameters. But in fact, the other Painleve equations is degenerations of the Painleve VI equations. We have the coalescent structure 65, 4, 2, P31, P32, 1. Such strange notations is historical. So from the modern point of view, that the thing which was called Painleve III equation should be divided in 3 types of equation. Okay, so. So in fact, this classification, this coalescence will fall a bigger classification, so-called Sakai classification, which is which will be the final goal of my series of talks. And for the difference case, we will speak. I think for the differential case, I think we will speak about mostly about Painleve VI equation and Painleve IV equation. What means the closed sense? It's very simple. So when we want to go from, so I will present the class, because we are working with these two equations, I will present only this class, this part. So, so to move from Painleve VI to Painleve V, we should just take T6 parameter, rescale it by epsilon, u equal epsilon t q6 epsilon t q5, b6 b5 divided by epsilon to preserve the symplectic structure, of course, and theta 1 equal 1/2 epsilon minus 1 plus theta star, and theta infinity 1/2 epsilon 1 minus theta star. And after the substitution, 10 epsilon to 0. So we see that, and finally we have Hamiltonian like this: TH5 equal to P plus T, PQ, Q minus 1, plus 1 minus T theta 0 minus T theta T, PQ. Plus 1 minus theta 0 minus theta star, q minus 1 plus q plus t theta 0 plus 1. So is there some questions? How this rescaling is done? Okay, so and the second rescaling from B5 to B4. Is a bit more complicated. Q5 equal 1 plus epsilon 4 and q p5 equals to p 4 divided by epsilon. Theta 0 is minus epsilon minus 2 over half. Theta star equal to epsilon minus 2 over half minus a2 minus a1 over half. And theta t doesn't scale. So finally we take Hamiltonian of the 4, which will be, we will speak about this equation for the remaining part of the seminar, and maybe surely for the some first part of the second seminar. So here we obtain some rather simple Hamiltonian. And the equations, now I will write the equation because we will use it, which are as follows. Okay. So, so we see that so now we finish the first part of my plan about Painlevé equations. So this is brief. This was brief introduction how they appear from this monodromic deformation and how they are connected to each other. So and now I'm moving to the second part of the plan, blowups and resolutions. So and in this part I will tell what is the space of initial data and what is the motivation to study this space. So let's see what we have here. Here we have some dynamical system, and in right hand side we have polynomial coefficients. So we have no zeros in denominators because no denominators. Yes, and we can ask question: Can we reach infinity for one of the variable q or p or both? Can we reach infinity for the finite time of our evolution? So, for example, can we reach v equal to infinity? So to do this, to see it precisely, let us make change of variables. So q0 p0 will be q1 over p. So we just invert what we will have. We will have q prime say 1 plus 2 q over q0 over p0 minus q0 square minus q0t, and here p0 equal to minus a2 p0 squared, yes, minus 1, I think, plus 2 p0 q0, minus 2 p0 q0, and minus p0 t. Yes. Sorry, there is plus. So we see that actually the answer is yes. Why? Because if we look at this equation, if we are in a point where, for example, b0 equal to 0 and q0 equal to 0, but on the directions of p0 divided by q0 is some lambda, we will successfully move from this point to the map where p0 is not already infinity, where p0 is not already 0, so it is already p not equal to infinity, so it's our initial map. So so we see that for some initial data, because the evolution is of course invertible, we can reach the point infinity, but only for q equal to 0.
So essentially you are saying that you evaluate p0 prime and q0 prime at p0 equals 0 and q0 equals 0. With that condition you get that it is different from 0.
Yes.
And then you can move away from that point.
Yes. So, and of course, because I can invert the dynamic, so this means that I can reach point infinity.
Yeah.
For p0. Okay. So and also we can do the same. Inverting also q and both q and p. So we see that that in fact all of our trajectories can be put in p1 over p1. Yes, because every trajectory which reaches infinity, so infinity it's like for this equation, infinity is a singularity, but it is a removable singularity because at the next moment we will move away from this point.
Actually, it's this argument is a bit unclear. It looks like it's insensitive to the coefficient in front of p0 in front of q0 or p0. But let us just try to see what happens with this solution. So, suppose everything is regular in the second equation, so P0 vanishes linearly in time. Yes? And if we substitute this into the first equation, say that P0 is some constant times t times t minus t0, and then we get that q0 should be some power of t minus t0. Yes, so. And this power is dependent first on the asymptotics of P0 around it's 0, but probably it's 1 because all the terms except for 1 I think will vanish. So asymptotics of Q0 should be in this case like t squared. So it's not P0 over Q0 equals to lambda, but something like P0 squared over P0 equals to lambda, and it's sensitive to the coefficient.
What coefficient? This coefficient?
No, in a coefficient in the equation, like this 2.
So when we are at this point, we have that P0 prime is 1. Yes, because this all vanishes.
Yes.
And here we have something like u0 prime minus a1 plus 2 lambda. That's all. Yes.
So, wait, how do you know that? No, in this case, so you have P0 and another variable is lambda, because how do you know that there is a solution such that the ratio tends to something? We should impose a new variable lambda and write an equation for this variable and show that it tends to some constant.
Yes, of course, we will do that. So you just explain what problem we are. So we are we should move to some new coordinates. Yes.
I'm trying to say that it's just not true that q0 or p0 should equal to some constant at this point. It seems that it should go to 0.
Yes. In fact, I think that you are right, because here you have you need 2 blocks to resolve it. Yes.
And just look at this equation. If you know that P0 prime is 1, it means that P0 equals to t minus some t star.
Yes.
And if you substitute it to the first equation and look at the main asymptotics, it says that Q0 is t minus t star squared.
Yes. Certainly. Certainly. Yes. And we will see. Okay. So yes. Thank you, Pasha. So now we just say that so I think is it around too fast? Yes. So this is not correct for Painleve 4, but for more simple case it will. Yes. So where we are, we see that we can reach infinity point. So we can try to cover to put all of our trajectories P1 over P1. But what is called the space of initial dot? We want to construct the space through each point. Through each point of the space. Only one trajectory goes through this point. But for when we put our trajectories in P1 over P1, this is not true, because we see that the solution naively because of Pasha remark depend on the ratio of Q0 divided by P0. Yes.
P0 squared, probably.
Sorry?
Probably P0 squared.
Yes, that's right. But I say naive. So we should do something with this. So now we will move to some toy exam, which will not have the such issue as Painleve IV. So finally, I can say that through the point Q0 over P0, there are we see that through this point a lot of trajectories pass infinitely many. Yes. This you cannot refuse. Okay, so let's take very simple dynamical system. Yes. So let's see. What is the trajectories of this or of the dynamical system. What is the trajectories? How can I draw it?
Who knows how to solve such equations explicitly? Like, what is the general solution?
Yes, what's the general solution?
What is the general solution to the first equation?
Okay.
Probably no. There should be some questions like if is Anton's notation clear or not? Like,
So prime. Okay. But prime is it's like
but dot was not.
okay. Prime is d over dt. So there is some evolutionary variable. In fact, x equals it, and y. What will be the trajectories?
Also, who can tell what is the solution of the first equation, then of the second?
No, maybe it's better to think about the second.
Well, but
The first equation is t plus constanta.
yes.
And the second equation, there is like a logarithmic derivative of y, right? So it should be exponent of
What?
minus.
No.
So can you say?
They are lines.
Sorry.
Lines. That's the difference.
Also, can you just say what is the solution? Like x equals and y equals.
X is t plus a constant.
Yes. Well, can you write?
X equal t plus c0.
Yes. And y is.
Then we have log y is log of t plus c0.
Yes.
Y is t plus c0.
Plus some other constant. Yes.
Some other constant. So finally we have the solution of this equation. The general solution is C1t.
Well,
And
t
C1
plus
is-
c0. And
Yes,
can
you
also
can
mention,
substitute.
we can also mention that if we put some alpha in this equation, then we will have x to the power alpha.
But we don't want to do this. So the trajectory is very simple. It's just lines, which depend on the constant C1. So this constant is rather unessential. It's like some normalization. So we see that all trajectories start or meet in the in the center of our plane. And also we have that through this line, which is x equal to 0. Yes. There are no trajectories. So through x equal to 0 except the point 0, 0, it is an inaccessible point for our dynamics. Yes.
Is it only because we prefer to study only coordinates x and y everywhere? Because in principle we could say that the system also lives on the p1 times p1, so in this case we would allow coordinates 1 over x, 1 over y, which could be used this line. Is it or not?
Yes. So if we check if we take another coordinates like p1 like you say, then we can of course assess also this. No, because here you have this equation. Yes. So you cannot stay on the line x equal to 0.
No,
It's not symmetric. I think that's why it was written in this manner.
Yes.
Okay, so we see that this line is a necessity, and we want to construct the space of initial data for this simple system. How we can do it? Because the initial data at this point essentially depends on the direction which we come to this point, we can introduce new coordinates, which is x over y. It is will be, we will call it x1 equal. So and let us rewrite our equation to these coordinates. So what we have that so I forgot maybe. I constantly forgot which map is better to start with. So x equal to 0. No, sorry. Yes. My first choice was more convenient for us. No. No, it's correct. Yes. So what we have? We have that yes, and take x is not 0. So we have that y is equal to 1 no, not x is not equal to 0, but we are not on inaccessible. We are not on inaccessible point. So y1 is 1 over x1, yes, and prime, and x1 prime is y prime, so it's 1 over y minus x over y squared over x. So we see that it is 0. It is 0. So so finally we have in these coordinates we have the following dynamical system. So y runs. So x is constant, and y runs in this way. So no, maybe. And this line is inaccessible. This line is inaccessible because it's line where x1 equal to 0. This means this direction. Yes. I'm sorry, but finally I choose inconvenient method. nevertheless, you should use it also. We can also take another set of coordinates. It's like it will be x over x. So we have that x prime equal to 1, yes, and y prime equal to x2 prime equal to 1, y2 prime equal to x prime.
Oh, we know that it's 0.
Sorry?
We know that it's 0 from the solution, right?
Yes. Okay. Let me not calculate. Yes, so it's 0. Okay, so we have the following picture. We have the following picture, and there is no inaccessible divisor because in this map this cannot reach infinity, where this inaccessible divisor lives.
So we have one point when x equals to 0 and where x also tends to 0. So in principle there is a point 0, 0 at this plane, which means that y tends to 0 faster than x.
Yes. Yes, but if y tends to 0 faster than x, so let me think. So if you talk about this point 0, 0, then we have that y is more close to 0 than x, and I think that this is just the line y equals to 0.
It's not essential. We have a line x equals to 0 at this picture, but it corresponds to the point to the point 0 at that picture, because all the points of these lines correspond to endpoints of all trajectories.
You say, when I say about line x equal to 0, I say without point 0, 0, of course.
Yes.
The set of inaccessible points, which is x, let me denote it t. It is x equal 1, x equals 0, but y equals 0. Okay, so you see that we have in fact constructed the space of initial data for this toy dynamical system, and this space consists is obtained by gluing two maps, this one and this one. And you can very simply calculate the transition function. So x2 is just x1 y1 1 over x1. And you see that for every point except the point 0, 0, this is one to one correspondence to the initial plane. Yes, because if both x and y is not 0, it is obviously, and if x equal to 0, we should use this map, and if y equal to 0, we should use this map. So we see that we glue inside the plane, we glue in the point 0, 0, we smoothly glue some projective line, yes, which is given in this coordinates as x2 equal to 0, and in other coordinates it is given by y1 equal to 0. And this procedure is called blowup of the plane. For the real case, it could be not algebraic, but from the smooth point of view, this procedure could be seen as follows: we take the plane and we go from the plane to the one rotation of the helicoid. I think I cannot draw it. I needed to train, but I will just write some formulas. So you can make the following. You can make the following.
The sign probably. No.
Yes. Of course. Sine and z. So you see that yes, and phi is from 0 to 2 pi, one rotation. So phi. So you see that we have two parameters, and if u is not 0, then there is only one point with given x and y. But if u is 0, then there is a whole line 0, 0, phi. Yes, on this surface. So this is the procedure of blowup, and using this procedure, we will construct the space of initial data for the Painlevé equation, but I think we should do this next time.
Yes.
So thank you for your attention. Some questions?
questions?
Comments, remarks?
Can you repeat how we define the blowup because I don't get.
So, what is definition? We take two maps. This one. So the blowup of the plane is the manifold. Of the plane is the manifold, which is constructed in the following way. We take two maps, which is written here. How it connects with the initial plane, and we take two maps with such a transition function. So this manifold is called blowup of the initial plane in one point.
So we can imagine it so why is it called blowup? Because we take initial plane and remove one point of it and replace this one point in the complex case with a complex sphere CP1, which parameterizes the directions of lines going to this point. So if if we take a non-blown up plane and try to go to this point 0, we will just get to this particular point. And on the blow-up, we will come to different points of this CP1, which is inserted inside of instead of this one point.
You should mention that after the blow-up, the lines, for example, x equal to 0 and y equal to 0, does not intersect anymore. This was just was our aim, because trajectories here is lines.
So probably one can draw a small circle around this 0 and show where the circle on these two pictures, right?
Yes, that's right. Let's do this. So here is a circle. Okay, so and here and this circle is like RP1, yes. And here and we take the maps. Sorry.
And just to draw it in these pictures.
Yes, I want to do it just now. So this corresponds to the map of RP1 when we remove these 2 points, and so this circle is just how can I? So when we have it's like
one of your coordinates is y.
yes.
And it is always close to 0 because the circle is small, and another
Yes.
coordinate.
Yes, so it runs. It's like something like that. I think it's like a tangent function, but very with very very low. very risky. And it is on this picture, and on this picture, on the second picture, it will be the same force, like
probably it's orthogonal to this line.
yes, of course, because this is the same track. Yes, certainly. Yes, so it will be something like that.
So actually it can be given by in the equation. It's like x1 squared y1 squared plus y1 squared equals to 1. Yes.
So it will be like tangents, I think. Yes.
No, like 1 over the square root of 1 plus y squared. Oh, but anyway, it should be clear.
So what is the question, sorry?
Which is
Hmm.
which is the equation of the curve? It will be an hyperbola. What is it?
Oh, no.
So if you want to calculate,
Oh, we can just substitute like x equals to x1 times y1. Yes.
plus 1 equals f squared over x squared. So it means that x1 squared equal 1 plus 1 equal r squared over y1 squared.
Mm-hmm.
So y1 it is r over square root of 1 plus x1 squared.
Mm-hmm. So something happens around there, but it goes to 0 at infinity.
Yes.
It's more or less a straight line. And initially it was something small.
So we can this way, but something like this.
And when r goes to 0, on one picture we get just a point, and on the other picture we get this a line.
It should intersect all the tractors.
Hmm?
It should intersect all the tractors.
Mhm. And it's actually interesting to study it in the complex case. Because it's a way to compute so-called self-intersection of this a new line which we insert. So,
Yeah, but we'll so you think that we can find geometrically that
yes, of
self-intersection.
course. Turns out that we cannot deform it in complex analytic way, but we can deform it in non-analytic way. And,
Yeah. Okay, so
by the way, in the real case, what is the self-intersection of this line? Is it? It's of course modular 2, but is it 1 or 0? Probably it should be 1.
Yes,
No.
I think it should be 1.
Mhm.
I don't know.
Mhm.
Maybe I don't know, maybe there is some map from the complex to real case.
Mhm.
I don't know. Okay, so maybe let's
We resume next time.
yes, we resume next time and postpone.
Which will be the 28th
Yes.
of March.
Yes.
Let's thank